In this exercise, we're being asked to convert a set of symmetric equations back into a set of parametric equations, and this represents a line in three-dimensional space. So if you will look here in blue, you'll notice that these equations don't depend on a parameter t, but in parametric form, what you'll have is the x, the y, and the z independently defined in terms of a parameter. So what we have to do is somehow introduce a parameter and write the x and the y and the z independently from one another. Now, if you remember how to go the other direction, it was actually pretty straightforward. What you would do if you had a line written in parametric form was you would solve for t, and solve for t, and then once they're all three set equal to t, then you would set all three of them equal to each other to get your symmetric equations. Well, we're going to do just the opposite to put it back into parametric form. So we'll take x plus 1 over 9. We'll set that equal to a certain parameter, and y minus 5 over 2, which equals t, and 2z, which equals t. If all three of these are equal to each other, then all three of these would all be equal to, some t value. And so once we set all three of these equal to t, we're halfway home. We almost have it set up in parametric form. Now we just have to solve for x, y, and z respectively. So this guy, and I'm going to skip some of the basic algebra, this would lead us to x equals 9 times t. You multiply the 9 to the right hand side. 9 times t minus 1. We'll subtract that plus 1 when we're finished multiplying by 9. The y value would be equal to 2 times t. Multiply 2 to the right hand side plus 5. And lastly, the z would simply be 1/2 t. 1/2 t. So we're done. This is again the equation of that line in parametric form as opposed to being written using symmetric equations. Now, I know they didn't ask us for this, but just in closing, let's do a little extra. There's some things you can read off looking at the equation of this line in parametric form. For example, the AT, BT, and CT, this ABC right here, indicates a vector. We'll call it vector v. This vector v, which in our case is 9, 2, 1/2. If you remember, this is the direction vector for the line in three-dimensional space. That's the direction the line is headed. And then there's a point indicated as well, -1, 5, and 0. So -1, 5, 0. That's a point that your three-dimensional line goes through. So it goes through point P in the direction of V. And actually this gives a good reason for why you might want to write a line in parametric form instead of symmetric equations, because in this symmetric form right here, you can't really tell what the direction vector for the line is or a point that your line goes through, very quickly.